we were working on the add method that we're going to create for our fraction class. So two fractions must have the same denominator to be added. The easiest way to make sure they have the same denominator is to simply use the product of the two denominators as a common denominator, so that a divided by b plus c divided by d equals ad divided by ab plus cb divided by bd, which equals AD plus CB quantity divided by BD. So I hope you got all that with all the letters. The implementation is shown in listing 1.5 on page 33. The addition function returns a new fraction object with the numerator and denominator of the sum. We can use this method by writing a standard arithmetic expression involving fractions, assigning the result of the addition, and then printing our result. So let's put this into our program here. There we go. So we're going to create a function here, or a method here, def, underline, underline, add, underline, underline. And we're going to have self, and then they call it other fraction. I'm just going to call it other, so we can keep it a little bit shorter here. Okay. We're going to need a new numerator. It's going to be equal to self dot numerator times other dot denominator plus here, I think I got to do a backslash here. Self dot denominator times other dot numerator. Okay, that gives us our new numerator. Then we're going to need a new denominator. So our new denominator is going to be equal to our self dot denominator times our other dot denominator. So once we get that typed in, what we need to do is return a new fraction object. So fraction, new numerator, new denominator. Okay? So let's save that, do a Control S to save that. I'm going to go back over to our program here. And I already have in here the frac 3 equals frac 1 plus frac 2, and print frac, now I want to print frac 3, okay? So let's see what happens here when we run this. We get 6/8, which is what the answer is, but it's not reduced down. We still have to do that yet. But if you think about it here, go back over here, we take 1/2 and 1/4, what we're going to use as the common denominator is going to be 8. So we take, let's see here and get the code here. Let me go back over here. Okay, so we have self is going to be the 1/2. Other is going to be the 1/8. So we take the numerator from self, which is the 1, times the denominator for the other, which is the 8. So we have 8 plus the denominator for self, which is 2. Oops, sorry, let me back up here. Numerator 1, denominator 4 is 4. Numerator 1, denominator, or denominator 2, numerator 1 is 2, so the 2 plus the 4 is 6. So that gives us our new numerator is 6, and then we take the two denominators and multiply them. The 2 times the 4 is 8. That's where we get the 8. That's where we get the 6/8. Okay? So let's go back into here. So we did this. I just used a little different variables on there, but we got the same answer there. So the addition method works as we desire, but one thing could be better. Note that 6/8 is the correct result, but that it is not in the lowest terms representation. The best representation would be 3/4. In order to be sure our results are always in the lowest terms, we need a helper function that knows how to reduce fractions. This function will need to look for the greatest common divisor, or the GCD. We can then divide numerator and denominator by the GCD, and the result will be reduced to lowest terms. The best known algorithm for finding a greatest common divisor is Euclid's algorithm. Euclid's algorithm states that the greatest common divisor of two integers m and n is n if n divides m evenly. However, if n does not divide m evenly, then the answer is the greatest common divisor of n and the remainder of m divided by n. We will provide an iterative implementation here. Note that this implementation of the GCD algorithm only works when the denominator is positive. This is acceptable for our fraction class because we have said that a negative fraction will be represented by a negative numerator. We're not using negatives anyway, so it doesn't make any difference. Okay, so here's the method. I'm going to go ahead and get out of this, and we'll do it together in our fraction class here. Now, the way the book does it is that they put it as a global method outside of the class. We're not going to do that. We're going to put it inside the class, and then we'll get it to work that way. So DEF, GCD, and let me get my code here. And what we're passing in is M, is M and N, okay? So in here, while M mod N does not equal 0, old M is going to be equal to M, old N is going to be equal to N, M then is going to be equal to old N is going to be equal to old M. Oh, no, we don't do that, sorry, wrong thing. M is equal to old N then is equal to old M mod old N. Okay, and so then when that gets down to where M mod N does not equal 0, or does equal 0, then it will break out and we will return N. Okay. So now, in our add method, we need to add a couple of lines in here. And let me see if that's, yeah, let's do this here first, and then we'll. So now we can use this function to help reduce any fraction. To put a fraction in lowest terms, we will divide the numerator and the denominator by their greatest common divisor. So, for the fraction 6/8, the greatest common divisor is 2. Dividing the top and the bottom by 2 creates a new fraction 3/4. This is in listing 1/6 on page 34. So that's what we're going to put on here now. So let me get out of this. Go back over here to fraction. So in our add now, we got our new numerator and our new denominator. We're going to come up with our common, which is going to be equal to self.gcd new n new num and new den. Okay. Then once we have those, then we're going to return our fraction with our new numerator, integer division, common, and our new denominator, integer division, common. Okay? So like I said, when we get the, with the 6/8, when we get the 2 as our common, then our 6 is divided by 2, which would be the 3, and our 8 will be divided by 2, which will be the 4, so we have our 3/4. So let's see how this works. I'm going to save this and then go over to our test program and do a run on it. Oh, got an error here. I must have mistyped. And I don't do that very often, do I? Right here. There. Uppercase GCD there. So resave this. Back to our program. Okay, so I got a problem. I think I messed up on over the right place here. I do this every once in a while on stuff too. Yeah, GCD needs a a self there. Okay, every once in a while leave that out. So again, save this. Go back to our test, and there we get our 3/4. Okay, so. Okay, so that's what we just did there. I'm going to go through this, and then we'll do this in the last lecture here. So our fraction object now has two very useful methods. They're shown in Figure 616 on page 34. An additional group of methods that we need to include in our example fraction class will allow two fractions to compare themselves to one another. Assume we have objects f1 and f2. f1 equals f2 will only be true if they are references of the same object. Two different objects with the same numerators and denominators will not be equal under the implementation. This is called shallow equality, and this is in Figure 7.1 on page 35. Okay, so you can see that here. Whoops, wrong one. Need 7 or 1, 7. That up here. Okay, I think I had the wrong page number there. I think this is what we're looking at here. Yeah. Okay, so we have F1 is pointing to the 3/5 here. And if F2 is pointing to the same one, okay, and then we do the equality thing on here, okay, then it's true because both of them have the same address pointing to that. But if we create two separate objects, F1 and F2, they are not pointing to the same one, okay, so that would be false. But even if they have the same values in there, it would still be false. Okay? So we need to be able to fix that. So we can create a deep equality by the same value, not the same reference, by overriding the EQ method. Okay, and that's what it's showing in here. That's what we're going to be doing now. Instead of by reference, we want to do it by value. We can create deep equality by the same value, not the same reference, by overriding the equal method. Equal method is another standard method available in any class. Equal method compares two objects and returns true if their values are the same, false otherwise. In the fraction class, we can implement the equal method by again putting the two fractions in common terms and then comparing the numerators. This is in listing 1.7 on page 35. Second, I'm trying to find it in my book here. Things aren't matching up with page numbers. There we go. I found it. It is on page 35. Okay, so let's put this in our class. There we go. Things aren't working the way I want them to for some reason, but we're getting there. Okay. Okay, fraction class. We have our DEF, underline, underline, EQ, underline, underline, and then what we need to do here, we have self and other that we have to pass in, okay? First numerator is going to be equal to self.numerator times other.denominator. And second numerator is going to be equal to other.numerator times self.denominator. Okay? So that gets those equalized on there. And then we can return first numerator equal second numerator. Okay? So that's going to work here. And we'll test it out here real quick. Go to our test. And I'm going to add, do it up here. Fraction 4 is going to be equal to fraction 1 comma 2. So we have ones that are equal. And so then down here I'm going to print let me see, let's do 1 equals 2. So we'll do frac 1 equal frac 2. And then we're going to print 1 equals 4. So frac 1 equal frac 4. Okay? So let's run this. And we get, whoops, that shouldn't have been false on that second one. Okay, I must not have saved this because it had an asterisk next to it. That may be what the problem was. There we go. That was what it was. I didn't get it saved. So on the first one, we should check frac 1, which is 1/2, and then we check the second one, which is 1/4. They are not equal, came back false. Then we checked the 1/2 and the 1/2, and that came back true. So now the equality works are on that. Back over here. So in the fraction class, we can implement equal method by again putting the two fractions in common terms and then comparing the numerators. This is, like I said, on page 35. It's important to note that there are other relational operators that can be overridden. For example, the LE, less than or equal functionality. The complete fraction class up to this point is shown in figure 37, or shown on page 37. So you drop down here in the book and you can look at that. The one that they have here, like I said, has the GDC outside the class. I put it inside the class. But that they have the INIT, the STR, the show, which we're not using, so I left it out, and the add and the equal. Okay, they then put some code inside the class. I'm sorry, inside the same program, the same file, but outside the class to test it. I used a separate program to do that. So that actually ends the chapter on this. So let me know if you have any questions. And we will be going. I'll be going over an example here in a little bit on the next lecture on doing some of this stuff. So if you have any questions, let me know, and then we'll be getting into chapter 2 after the program assignment and quiz over this chapter. So any questions? Let me know. Bye.